Welcome. In this video, we are going to start our section on geometry. In this video, we are going to look at points and lines and planes, and then put some of those points and lines together to make some angles. So our learning objectives for the first part are going to be to identify and describe points, lines, and planes, and then we're going to learn how to express those items using proper notation. And then finally, we are going to look at union and intersection of sets, although that's not going to be on your test. So there are actually different types of geometries. The geometry we're going to talk about in this course, and that you have probably only ever seen up until this point, is called Euclidean geometry, and because Euclid is the one who wrote all the fancy postulates. And I think there's 13? But like 4 are really important, and probably the most important one is not listed here, and that is about parallel lines. Basically, there's an infinite number of parallel lines when you're talking about Euclidean geometry, and they never intersect. That's what it means to be parallel in Euclidean world. Now, all the shapes are like your regular triangle, square types things, right? Your parallel lines never intersect like this and just go on forever. In non-Euclidean geometry, it's weird, like the parallel lines can kind of intersect, which is very strange, and like the triangles could be like puffy. I know it kind of looks like a circle, or it could be like wedged in like this, and they don't actually close, which is really weird, where for our world in Euclidean, our shapes are closed figures. Now, we're going to stay in the wonderful world of Euclidean geometry, so you don't have to worry about any of those fun shapes, but any of the fun stuff you see is probably in non-Euclidean and not Euclidean. So what are the things that make up the world of Euclidean geometry? How do we make all these fun shapes? Well, we got a couple of different items. We're going to start with points. So a point is kind of like you kind of think of it like a grain of sand. It doesn't have any width or depth or height or anything like that. So like a grain of sand, you put it under a microscope, technically has a width, right? Technically has a weight, but not in a real world application. So if you kind of want to take that idea and extend that to real world, theoretically, these points are just pinpoints in space without a length or a width or anything like that. So I know it looks like you can measure the length of, the width of that circle. You can't. We label them with capital letters. It does not need to be in order. You can see all of these are AB. I could have used AQ if I wanted to. It's just usually capital letters that we use. Now, if I take a bunch of points and I kind of overlap them, I line them all up in a row, then I'm going to get a line segment. To define a line segment, you're going to use the end points, so A and B for this one, and then you put a little line on the top of that. Now, if I would have had another point like this, C, oops, I lost my C there. AB would just talk about this part. If I wanted to talk about this whole piece, that would be AC. So if I stop at B, this part gets thrown out. If I want to just say BC, then it would just be this part. And so you use these two endpoints to name it. Since they both stop, and both, if you flip it upside down or backwards, they both look the same, I also could have labeled this BA. That's fine, as long as I put the little line segment up at the top. Now, if I take my points and I decide, you know what, I'm going to go off forever in just one direction. I'm just going to keep putting down points forever. And this time I'm going to go this way. Then this is still an endpoint at A, but B is like I'm just busting right through B, and I'm going to just keep putting points out forever. And you can't put things forever, so we put an arrow at the end. This is called a ray. So this has one kind of like a start point, but no stop point. The start point is going to be the side that gets the no point here, right? Like there's nothing there, where this, although it's hard to see, has a little arrow on top. So this is ray AB, where I'm not stopping at the B, I'm still going through, so that gets the arrow. If I write it the other way, right, if I have it extending going this way, or if I write the arrow pointing in that direction, I'm actually talking about this. So these two things don't say the same thing. You could write like BA like that, right? Because that would, I'd still be heading towards the B forever. We just usually start with the end point. You write the, it doesn't really matter though which way you want to write it. So as long as the arrow is with the side that is infinite. Now, if you're going to keep lining up both directions forever, and so both sides get an arrow, then that's a line. And lines are infinite in both directions, and because of that, you can kind of have whatever you want on here. So I could have called this like a line AC, if I had a C in the middle there, because it's going past the C forever. I mean, usually we use the ones that are furthest out at the end, but this is not technically wrong. It's just that this is a better name. And you can see at the top here, both of these have little arrows, where this only has one little arrow and that has a little arrow. Lines can also be named with lowercase script letters, like an L or an M, or you can put it like an L1 and an L2 if you have multiple ones on there. It really kind of depends on what you're working with. Now you can do half lines in either direction where you kind of have this open dot here. The difference between this one and this one is that the B is not included. It's kind of like you start here, but you don't include it in the set. It's kind of like a hole in the floor. So like the hole in the floor is in the room, but you can't stand on it kind of deal. That's kind of what that means. So if you see holes in algebra, it means it's there, but it's empty. Like there's a hole. There's a hole. It's empty blank space. We are not going to worry about that in this course. If you've done any intermediate algebra, you've probably seen some stuff like this before with piecewise functions. We're going to just talk about these fun pieces right here. Now, if I was going to plot, staying with the algebra thing, these points on a grid, a Cartesian plane, this is something that you've probably seen before. So if I wanted to plot a point on a 4-quadrant grid, I got my x-axis, I got my y-axis, where those two things intersect is called the origin, and that's the 0 on the x and the 0 on the y. So that point, the origin would be 0, 0. And points are always given the same way. It's x and then y. But that doesn't mean you got to plot the x first. Most people do, but you can plot the y first. So let me look at 1 here. If I was going to plot 2, 4, what most people do is they start at the origin and say, or go over to the 2. 1, 2. Okay, now what? Go up to the positive 4. 1, 2, 3, 4. Make a point. I'll label that point A. If they're negative, start at the origin, just do the opposite. Down to the negative 2. And then this one is still a positive, so I'll come this way. That's point B. Now, if you have zeros, it just means when you get to that part or that axis, you're not going to move up or down. So this says 5 on the x, so 1, 2, 3, 4, 5, but not up or down at all, so I'll just stay right here. Now, I guess I'll just go ahead and label that C, like that. Again, not an algebra class, not a geometry class, but now you know how these pieces kind of come together in a 2D plane, somewhere where there's a left and right and an up and down. How do we label these things in space when it's just lines and segments and rays? So let's say I have this full line here, right, DF, but there's 3 points on the line that I have labeled D. Let me see if I can move this off for a second, right? D, E, and F. If I wanted to define segment DE, I would have an endpoint on D and an endpoint on E, and I would just connect those two together like that. And then I can name it DE with a line on top like that. Or I also could have said ED if I wanted to. That's also fine. They're the same figure. Now, if this piece is going to go on forever and I want that full line, most of the time we use the ones that are out on the ends, the outermost end. So this would be DE, and then you can see up here, I have the line on, the arrow on both ends. I could have said DE with too many little, I don't even know what you call those things that make up the E. I could have said something like that. It's just we usually use the thing that's the furthest out. It's not technically wrong. It's just like this is a more accurate way to describe it because F is further along than E on this. And so D, E, and F, that would include all of these points. Even though the E is not listed in this one, it's wedged in between. If I only wanted to go one direction forever, then wherever I start becomes the first part here, and then I go forever the other in that other direction. I'm going this way, but this is my second point, so it looks like that. Now I could have said, I don't know, I mean, you could have written it like that, but we just usually start with the end point and then go to the forever, and then you just flip the arrow. Either way is fine. So we got points, we got segments, we got rays, we got lines. I'll be honest, rays, not all that popular out in applications. Usually you're talking about looking at lines and then breaking up those pieces. Now, if I have more than one line, I got a few things that could happen. I can have those two lines intersect, or they cannot intersect. If two lines don't intersect, those two lines are parallel. So I got line 1, you can see that that is an L sub 1, and then I got the L sub 2. They're never going to intersect. It has the same distance between the line, D for distance, the whole way through. If my two lines intersect, it could be that they intersect any old way, you know, like weird like that, or lopsided, or any of those, or it could be that they intersect in a special way that's called perpendicular, that creates this nice angle right here, which is going to be called a right angle. That's 90 degrees. Right, so you can intersect, you can not intersect. If you do intersect, maybe you're special. You could also be the same line where it's like you graph one and then there's the second one just lands right on top of it and intersects everywhere. But we're not going to worry about that. If my lines are intersecting or non-intersecting, I can talk about the different pieces that they make. So that would be a set of points that get created by all of these different pieces that come together. I could also talk about different parts of the same line when we break it all up. So set is just a fancy way in mathematics to say a collection of something, and the way you collect things can change. And depending on the type of things that you're looking at or the type of course that you're in, unions and intersections could be messy things to work with, or maybe they're not so bad. It's a little odd to talk about it in a geometry unit, but we're going to kind of use this to kind of help us wrap our minds around what it means to overlap in space. So a union means that things, you're looking at all the things that it has in all of the sets. So the two or more sets, and they all come together. So it's in A, and then it's in B, and so it comes together, so now they're all in A and B. An intersection only looks at the stuff that's in A and in B. So if I was looking at normal set theory, right, this would be A, and then this other circle is B. This piece right in here would be the intersection. I'm in both, right? I'm in A and that's a little upside down U, kind of can make it look like an A for and. That would be this piece in here. You're in A and in B. The union is more like an or, like you're in A or you're in B. So I would just list all the things that are in here. So what the heck does this mean? So let's say I have this line, and this line has 4 points on it, A, B, and C, D. And I want to find the intersection, right? Because this looks like an A, so for and, things that are in, what's that array? B, D, start at B, head out to D forever, like this, and then I'll get another color, and then I want to look at A, start at A and head to C forever. and there's AC. So this is a little strange, but you would have this overlap, since this goes on forever, where it is going to have B in common, right? So it has, let me go back out since I lost this. You see how this overlaps? This has both, this has both, this has both, this has both, right? All of this piece here forever. And so that is going to be ray BD, like that. A little odd, but that's why it's not on the test. What about the OR? I have AB, just a segment. I kind of like using this highlighter. Here's AB, right? Yeah. And now let's look at AD, which would be all of this. And it's a little bit easier to see that if I'm in OR, so I'm in either set, I'm in this or in this, well, that would be all of that fun stuff. So that would be A to D, which is a segment, right? Not forever, because these are segments. Kind of like this segment just got overlapped. If I wanted to talk about AB intersection AD, it's not a very exciting intersection. It would just be that AB right there. Like that. Now, if this line was kind of dragged down, you know, when computers kind of start to seize up and you drag something and it kind of leaves a trail. If you could imagine dragging this line down and it kind of leaves a shadow, like when you paint with something, like I take this and I drag it down, then I would have all of this in here shaded in. That's a plane. So you can think about a plane almost like a collection of parallel lines that are put so closely together that they overlap. So like you have this, right, like this super thick line that you've dragged up and down. And that's a plane. Now planes can also intersect or not intersect. And if they intersect, it could be that they intersect at a 90-degree angle, or they could just intersect any old way. We're not going to worry about how to name those types of things. It's just kind of an awareness that that could happen. They have all the same types of properties that you would find with lines. It just gets a little bit more complicated to name them all because you have so much more space. So what happens if we stay with lines and I have two lines and they intersect? It doesn't matter if it's a 90-degree angle or a perfect degree angle, but I got two lines and they intersect. Or maybe I got two rays that share an endpoint. Well, now what I've done is created some angles. So in this next part, we're going to look at how to identify and express angles with proper notation. And there's a couple of different ways that you can name and classify angles, and that's by their measurement or by using those endpoints. We're going to also look at some application problems, and then if I have a whole bunch of lines intersecting each other or intersecting each other in different ways, we'll look at what happens when I have a pair of parallel lines and a third line comes along and intersects it. So there's a couple of different ways that you can measure an angle. Degrees is the most common. If you were in a field like engineering or something like that, or maybe something more where you're focused on the mathematics of it, you might talk about radians. We're not going to talk about radians in this course. We're going to look at just degrees. Basically what a radian is when you get to circles, you'll take this little part here where you come from the center out to the edge. That's called a radius. If you take this and you kind of lay it like molding around the circle, right? You'll need 3 of those regardless of the size of the circle to, well, a little bit more than 3 to do half. So you'll need a little bit more than 6 to make your whole circle. We're going to talk about degrees. So an angle is either by joining 2 rays or you can have it where two lines intersect and then that generates the two rays, and then you get different angles that generate in there. We can name the angle with points. We could use just the shared endpoint, which is called a vertex. We can also name it some other ways, but this is by far the most common. It's pretty forgiving. I can say angle B here, since if I say angle B, there's only one of them listed here, so it has to be this angle right here. Or I can say ABC, angle ABC, or I can say angle CBA. The order doesn't matter, but if you're going to use all 3 points, the vertex has to be in the middle, so it partially matters, right? So I can start at the top or I can start at the bottom, but the vertex is always in the middle there. Now, if I had another one listed like this, I wouldn't be able to use angle B because do you mean this angle or do you mean this angle B? So if there's ones where more than one thing would have the same name, you need to use all 3. You can also talk about the measurement of these things, but just put a little script M out top. So this would be the measure of angle B, where the measure of angle ABC is, I don't know, 30 degrees or something like that. If I have this angle, you can almost kind of think about it like as if you had a line and you kind of squeezed it together, like put a little hinge in the middle there and open that up to make this like a bent line, right? You can think about a bent line that has a kink in the middle there. So if I didn't squeeze that together to make a point and it just stayed kind of looking like a line, or I took 2 rays and I put them together like this and it just made a line, that would have 180 degrees and that would be called a straight angle. So a straight angle and a line are essentially the same thing. The difference is, you see how it doesn't have like doesn't have those little arrows there? So that's why that would be a straight angle and not a line. So when you think about straight angles, you're kind of thinking of like something where there is a segment and it comes through like this, like some line cuts through it. If I take this hinge and I go halfway up in either direction, then that's a 90-degree angle, and that's called a right angle. When you see little boxes in the edge like this on an angle, that means that you know it's automatically a 90-degree angle. Things that have 90-degree angles are perpendicular. So if this was line 1 and this was line 2, I could say L1 is perpendicular to line 2. If I kept closing this, and I have an angle that's smaller than 90, but not 0, right? I didn't close the door all the way. I'm between 0 and 90. That's called an acute angle. And if I left the door open a whole lot, but not the whole way that it was flat with a straight angle, but more than 90 degrees, then that would be an obtuse angle. So acute is between 0 and 90, doesn't include either. And obtuse is from 90 to 180, but doesn't include either. So you can have like 179.95, but you can't have 180. You can have 90.23, but you can't have 90.00 for an acute angle. Now I could also take these angles, kind of like what you see right here, if I get some of this mess out of the way, and it kind of looks like I have 2 angles, right? Like I got this piece right here, and then I got this one over here. Like, so I got like 2 angles that share a ray. So it's like I took this ray and then I put another ray right on top of it. And then it kind of looks like that. So I have 1 and 2. So that would be called an adjacent angle. You can kind of think of like walls in your house, right? So if you have, where's my thing here? If I had one wall here and one wall here, right? This would be on both rooms, and then there's one room here and then one wall here, so you have that adjacent wall. It's the same thing with adjacent angles. So if I name this A, B, C, and then I have one here, D, This would be angle ABD, and they share a ray with D, B, and C. Now, I could just squeeze these together any old way where it doesn't really matter what their angles add up to if I was going to like knock down that wall. Or it could be that they come together in a special way where those two angles, when I merge them together and they overlap, that they add to 90 degrees. That's called complementary. Maybe I add them together and they form essentially a line. That's called supplementary if they add up to exactly 180. Anything else doesn't have a fancy name. Maybe they're not a bunch of rays. Maybe it's two lines that intersected and I have something that looks like this, where I got 4 angles. That's called vertical angles, and the ones that are like through the flip right there, like if you were to fold this in half, are equivalent. So in this picture, 3 and 4, they have the same angle measure, and 1 and 2 have the same angle measure. Creates 2 pairs of what's called vertical angles. So if it says, hey, you got a pair of complementary angles, you know that those two things add to 90. If it says, hey, you got a pair of supplementary angles, you know they add to 180. If they give you something that looks like 2 lines intersecting, then you know this one's equal to this one, and this one is equal to this one. So if I have something that looks like this, and it says solve for the angle measurements, not really, it should say that something like these angles are supplementary. It's not good practice to just kind of look at the picture and assume that you know what it's going to be equal to. But we're going to give them a break and say that we know that this is a straight angle right here, and so this must add up to 180 degrees. So then that means if I take 32x minus 7 and then add the 5x plus 2, that has to equal to 180. So now I have to remember how to solve equations. So let's look at this one before we go through an example written. I know I'm going to add these two things together. 32x minus 7 plus the 5x plus 2, that's going to equal to 180. Anytime that you have things inside of parentheses and there's nothing out on the front, it's like there's a little invisible 1 there. So I'm just going to multiply that through. So I get 32x minus 7 and then 5x plus 2. And now I can do something called combine like terms. So you both have x's. 32x's and another 5x's is 37x's. A negative 7 and it ate my little sign there, but that's a positive 2. If I owe somebody $7 and I give them back $2, I only owe them $5. So that's a minus 5. So now that side has been simplified. There's no other like terms right now because this has an x and this doesn't. So now what I need to do is get everything away from the x. I'm going to do the opposite of whatever this says here. So this says minus 5, so I'm going to add 5 to both sides. Negative 5 plus a 5, right? You've paid them back the $5 you owe them. That means that's a 0 now. And you're only left with the 37x. This side now is a 185 because I added that 5 to the 180. If you don't see an operation, it's multiplication. So that's 37 times x. So to undo it, I'll divide both sides by 37. And I get, well, 37 divided by 37 is 1. So that's a 1x. We could just write x. And 185 divided by 37 is 5. So x is equal to 5, but you're not done, right? X is equal to 5. This one's got 32 of them, and this one's got 5 of them. So now I need to find out what these angle measures are. I have to take these original expressions, take the x out, and put the 5 in. So this one's 153. This one is 27. I make sure they add up to 180 to make sure I solve this the right way, and then I'm all good to go. Let's look at another one. Solve for the angle measurements. This one's written a little bit better in that I have my little box there. So that means I know that all of these things that get pieced together right here in this section equal 90 degrees. So I'm going to try to write this as neatly as I can. I got 9x minus 5 plus a 4x plus a 7x minus 5. This is all equal to 90. All of these have 1's out front. When you have just 1's out front, basically what happens is that the parentheses just disappear. So 9x minus 5 plus a 4x plus a 7x, and that's a minus 5, equal to 90. I have lots of like terms. I got all these ones with the x's, so 9x, 4x, so that's 13x, 7 more, that gives me a 20x, negative 5, and a negative 5 is a negative 10. If you owe somebody $5, and then you borrow another $5, now you owe them $10. So this is a subtraction, so that means I add 10 to both sides. That adds out, I got a 20x. This is a 100. Divide both sides by 20. X is 5 again. But that you're not done, right? So now I got to plug in 5 to all of these things. So that's 45 minus 5. 4 times 5. 35, because 7 times 5 is 35. Minus another 5, that's 30. And all of that, hopefully, yep, adds up to 90. And if my scribble is too hard to read, that's what it looks like when it's all done. If you have vertical angles, and you know one, now you know them all. Because we know that vertical angles, like if you go through the bow tie, that's the way I always think of it. If I fold over through in the bow tie, that's 40, that means this has to be 40. But if I just look at this, right, and I just kind of ignore this part down here, and I just look at this section, well, I have a straight angle. And that's a line right here, right? That's a line. So I know angle 2 and angle 1, since they're sharing a ray, they're adjacent angles, but they're special ones. They're supplementary. And if you're 40, and this whole has to add up to 180, the rest of it has to be of 140. So that is equal to 140. Let me get rid of some of this mess. Not that mess. And if that's 140, then I come through the bow tie to go to angle 3, and that has to be a 140. It's always going to work like that every single time. If you know one, you know them all. Which one you find first, that's up to you. I like to find the ones that are already equal. So I usually go this way, right through to the other side. But you can work your way this way and then find that supplementary one first. Either way is totally fine. Let's look at an application of this. Live on the corner of First Avenue and Linton Street, and you want to plant a garden. So let me grab a picture. There we go. Looks something like that. And I know that the angle between Linton and First, right here's, this is Linton Street. It's a little confusing, I think, because it's got the width. So there's Linton Street. And here's First. And the angle between them is 150. What is this angle is the question. Well, they didn't want to know this, but I also could have labeled that 150, right? That's the corner of Linton and First also on that side. Well, if this is 150, and this pink line right here has to add up to 180, that means the rest of this section, this little pie slice right here, has to be 30. Because this is already 150 and 180 minus 150 is 30. So not too bad. What if there's a third line? This is 2 lines. What if a third one comes along? But it doesn't intersect both of them. It only intersects one, like this. Then you've got a pair of parallel lines. cut by what we call a transversal. And you get 8 angles, sort of. I mean, you do get 8 angles, but what you really have here is the same set of vertical angles twice. If I can, let me see, you can see that if you kind of just follow that line and transversal down, they're the exact same thing, whether you go up or down. So there's 8 angles, but it's really just that you get that same 4-pack twice. And as we know, that 4-pack is really a 2-pack, that's twice. So you have a bunch of angles that get created here, but there's really only 2 measurements. There's this one here, that's going to be for 1, 4, 5, and 8. And then the other one, which is going to be acute, or less than the 90 degrees, for 2, 3, 6, and 7. So if you know one, you know them all. And these pairs have special names. There are the alternate interior angles that are equal or congruent, right? 3 and 6 are the same. Alternate, because alternate sides of the transversal. Interior, because it's on the inside of the parallel lines. There is corresponding angles. That's the one that we saw that if you were to drag this down where they would land on top of each other. So 1 and 5 are corresponding. 3 and 7, 4 and 8, 2 and 6. And they all have the same angle measure. There's also alternate exterior angles. Alternate, opposite sides of the transversal, exterior, because you're on the outside of the parallel lines. So if I know one, any one of them, interior, exterior, alternating, corresponding, it doesn't matter. I know them all. So let's say, this one doesn't really look like it makes sense. So let's say angle, let's look at number 3 here. If angle number 7, the measure of angle 7 is a 60, right? This is a 60 right here. That means 6 is a 60. Looks like go. There we go, 60. 3 is a 60, and 2 is a 60. So all of these are 60 degrees. Well, this is a line right here, so then I have a straight angle that I know adds up to 180 degrees, making these supplementary. So if this is 60, then 1 is 120, 4 is 120, 5 is 120, 8 is 120, right? And if I went the other way and I said, well, what if 8 was 110 on number 4 here? Well, this is a 110 degrees, and so is 5. So is 4. So is 1. They're all 110. And if that's 110, well, all of this has to add up to 180. So I need 70 more. So 70, 70, 70, 70. And we'll always kind of like, you see how it kind of go zigzag? Always going to do that. So that's how you take points to make lines, and lines to make angles, and more lines to make even more